smaller. All right, so today we're going to talk about power. Um, and I'm gonna post some formulas. So there's the first formula. I suppose I could just write it down. I don't know why I want to be all fancy with it. So what does that mean? Well, the power of a system is power is, if you just read the formula, the power is the change in energy over time. Okay. And so 1 watt is equal to 1 joule per second. Okay, so 1 watt is equal to 1 joule per second, which makes sense, right? Because, so this is watts, usually a capital W. This is joules, right? Because energy is measured in joules, and time in a physics class is always measured in seconds. Now, there's some different variations of this formula. We said that energy is the same as work, right? So you could say it's work done over time. So you could say work over time. Another thing, now if you take this first equation and do some algebra, you could find that the energy, and this is a capital letter P, not to be confused with lowercase p. Lowercase p is momentum, capital P is power. It's kind of hard to keep track of, if I'm honest. And then there's a symbol that looks like a P that's used for density. And then I forget what we do for pressure. I think pressure is P2. So anyways, so power times time gives you the energy. Now this one is the same as this equation. It's just we did some algebra. We just multiplied both sides by change in time. I don't like how this T looks. There, that's the proper T. Okay? Get it? That's the property. Guys, I can't do this all day, you know. It's a lot of work to be this funny. All right, so let's see what that looks like. So here are some examples. Does everybody have this written down? So here are some examples. Well, maybe. Let me try this again. There we go. You don't have to write this down. I just want you to see it. A horse, so when they say horsepower, you know, I don't know if any guys are into cars or whatever, but when they say horsepower, it's about how much energy or work a horse can do per second, and it's about 746 watts. These fancy LED light bulbs that are, yes?
I was going to say that, did you know that horsepower isn't actually horsepower, because horses actually have 15 horsepower?
They have what?
Horses actually have 15 horsepower, so it's not a horsepower.
Yeah, it's weird. Just like a foot isn't really the length of somebody's foot, kind of. Yeah. But anyways, these are actual measurements for watts. Okay. These are Well, speaking of, so a student said that a horsepower isn't actually 1 horsepower. A horse can actually do like 15 horsepower. You gotta think there's probably like an average. There was probably a really tiny horse, and they're like, oh, this is 1 horsepower. And then there's like this big Clydesdale or a quarter horse or something. And then they're like, oh, wait a minute, we gotta rethink this. The same thing with a foot. A foot actually was probably somebody's foot at one time. I don't know the origin, but it was probably the length of somebody's foot, but whatever. But anyways, these are actual different types of power. So a car can do 75,000 watts. Now that's just 75,000 joules per second. That's what it could do. A person running is about 300 watts or joules per second. And if we have time, depending on how much time we have, we'll figure that out. So let's do an example problem, okay? So another thing I want you to write in your notes is that power, because and you got to remember that it's like delta E over delta T, or the amount of work that you've done over T, is a rate of change. It's a rate. Okay? So let's think of, oh, this is festive, considering that there's snow on the ground. We'll do this. Think summer. So let's assume that this beach ball weighs 1 kilogram. Okay? And this is Mr. Adams holding it. Oh, that's a horrible stick figure. I started to draw the legs, forgot about the body. So that's me holding it. Oh, no, that's not good. You guys know I like fresh kicks. I gotta remember how to do this. I think if there's a way that I can flip it. Where? Up here? Oh yeah, flip. Flip horizontally. There it is. Okay, that's about enough on that. All right, so now I drop the ball. It's right here, and then I drop it to the ground. Sometimes I have a lot of fun. Probably more fun than I need to. So I'm outside, just playing with my beach ball, no big deal. And I drop it, but it falls 1 meter. And it does it in the time that it takes, delta T, is 1 second. So then I can figure out the power, right, by figuring out a couple of things. If I do the energy over time, I could do that. or if I do the work over time, I could do that. So, and we're going to do two scenarios. The first time I drop it, T1, it's 1 second. The second time I drop it, I'm not quite sure. Maybe there's a big gust of wind, but it takes 60 seconds to drop it. Okay. So there's a couple ways you could do this. It's also equal to the work done over time. So to calculate the work, remember that the work is equal to the force times the distance. But in this case, the force is the mass of the object times the acceleration due to gravity times the displacement, which is really the height. Isn't that the potential energy formula when you think about it? So that's the same as the potential energy, which, by the way, we could just change this E. It's any energy. It could be kinetic energy, potential energy, all that stuff. So the mass of the object is, my beach ball is 1 kilogram. The acceleration due to gravity is what? 9.8 meters per second squared. Times the height, which is 1 meter. We did all that math to find out that the potential energy is actually 9.8 joules. And so the power of the first object is going to be 9.8 joules over 1 second. So that's 9.8 watts. That's how much power is generated or used or work is done. It's the rate of the work that's done over time. Okay? Can I slide this up a little bit? Okay. So now, in the second scenario, a gust of wind hits the ball. Well, the potential energy is still the same. I raise it. 9.8 is the joules. That's the potential energy. I raise it 1 meter. Gravity's still the same. The ball's mass is still the same. But now I'm going to do it over 60 seconds. If you plug that in a calculator, it ends up being about 0.16 watts. Now remember, watts is per second. So every second, the work that's being done over time is about, and another way to look at it is 0.16 joules per second. Okay? Does that make sense? I'll give you guys a second to finish writing all that stuff down. How many of you guys drew the Jordans on my feet? That's what I'm talking about, brother. All right. I'm just double checking the notes. There's a lot of notes in here. All right. Let's do some examples. Let me do one more example, and then I'll give you guys some homework. And plenty of time in class to get it done. All right, so an elephant lifts a 300 kilogram log to the height of 3 meters and in a time of 4 seconds. How much power is required? All right, so the first thing we got to do is what, guys? Yeah, we got to draw the picture. So I'm gonna this is my log that has a mass of 300 kilograms, and then the height that it's lifted off of the ground is 3 meters. And the time that it takes to do that is 4 seconds. So this is kind of easy. We could do, well, we're just going to do, for the power, we're going to do the work over time. That's a triangle.
Can you scroll up a little bit?
Yeah. Here, I'll move my face over here. So the power is going to be the work over time or the energy over time. Now, the easiest way to do this is what type of energy can we do if we have a height and we have the mass and we lift it? Well, that is U, potential energy. Okay? So, what's the formula for that? Well, remember that it's the mass times the acceleration due to gravity times the height all over, and we already know what delta T is, 4 seconds. So then we're going to come over here and we'll say the mass, which is 300, I'm running out of space over there. I don't like the way that looks. $300 kilograms times the acceleration due to gravity. G is 9.8 meters per second squared. 9.8 times the height, which is 3 meters, right? All over 4 seconds. So if you plug that into a calculator, we get that the power is equal to 2,200 watts, roughly. It ends up being like 8,820 joules over 4 seconds, and you get this. Okay? So 8,800 joules per 4 seconds. Does anybody have any questions? Let me just double check. Let's do one more, okay? I just want to make sure you have enough problems, enough examples to kind of guide you on your homework. And you guys are flipping those notebooks with some aggression. Fine, I'll write it down. All right. I gotta put my face back over here. So this says that a sports car, what kind of sports? We want a Lambo. No, I want a real one. None of this fake stuff. No, I think I want clip art though. That's an old one. That's a Ferrari, but that's okay. I guess we'll settle for the Ferrari. All right, so it says a 1,200 kilogram sports car accelerates from 0 to 60 in 20 at the rate of 27 meters per second in 5.2 seconds. What is the average power? All right, so this is the same problem, but now we're going to do kinetic energy. Okay. So let's let me. I realize I haven't been writing this down. So it's the change in energy over the change in time. What type of energy? Kinetic energy over the time, and we know the time is 5.2 seconds. Right, that's what the time is. So let's write that down. Delta T equals 5.2 seconds. We know that the car has a mass of 1,200 kilograms. We know that it has a velocity of 27 at the end, meters per second. Okay. So, anybody remember what the formula for that is off the top of your head? Well, to find the kinetic energy, it's 1/2 times the mass of the car times the velocity of the car squared. Or 1/2 times 1,200 times 27 squared. Now, if you crank through that math, you get that the kinetic energy. Oh, I can't write today. You get that the kinetic energy is 437,400 joules. Okay, that's the kinetic energy at the end of this thing. So now, in order for that to have that kind of kinetic energy at the end of this, because it had 0 kinetic energy at the beginning, that means that some work had to be done. Okay? Well, the amount of time that that work had to be done was 5.2 seconds. In other words, we're going to say 437,400 joules over 5.2 seconds. And that'll tell us the power the car needs. Well, if you plug that in a calculator, the actual power is 84,000. Man, I'm tired. It's Friday. Watts. And so, for funds, before I give you guys your homework, let's see what that is in horsepower, because that's what one way to check it. So we'll say 84,100 watts. Watts to horsepower. So 112 mechanical horsepower, which is not 112 horses. Well, you divide it, it's like less, right? Anyways. So it looks like, remember how at the beginning of this thing it said that a horse had 746 watts? See what the actual conversion factor is, 745.7. Kind of neat, huh? Anyways, that's all I got for you guys today.